All right. Hello, everybody. Thank you so much for coming to IEEE's PCB workshop. This is going to be the first of 4 sessions. So starting this week, every Wednesday, same time, hopefully same room, we're going to meet and then hopefully be able to start and finish a PCB with a specific design in mind when designing it. This time around, basically the goal is to be able to create a breakout board, which if you don't know, is essentially just a small PCB that has a specific chip or component on it that you can use as kind of something modular. It could be used for a lot of different things. So we're going to use in a small breakout board that has 2 motor drivers on it that will be able to control the speed and direction of those motors. So just to get started, a little background on me. My name is Adam, and I'm a first-year master's student here at CSU Long Beach in electrical engineering. I did my undergrad here as well, and I specifically took a liking to making PCBs. I've been doing PCB design work for about 2 years now, so it hasn't been that all long. So I'm by no means an expert, but hopefully, you guys can be able to get something out of this, at least get started and start moving forward with your designs. And just over the years, you'll start to learn it's really not quite as intimidating or bad as it initially looks or seems because it looks crazy. But once you get into the thick of it, you'll realize that hopefully by the end of this, that you'll feel confident enough to do your own PCBs on any design you like. So, in my opinion, PCB design is a ultimate test of your skills to be able to take a concept that you're interested in and actually apply it with your specific parameters that you want. It gives you total freedom to choose your different parts, choose your size, choose your parameters, choose your end goal, and your inputs. So you can create a system using commercial off-the-shelf parts that be able to pretty much accomplish anything you set your mind to. For example, if you're interested in power, here's an example of a power board that me and the other lead, Darian, did not too long ago. This is for a rocket. So if you're interested in power, it's quite easy to make your own power boards to be able to provide different voltages with different current limits and everything like that to different systems. Um, if you're interested in controls, I had handed out a little PCB with some wheels and everything around it. I handed around. So this is a project we used for Micromouse, which is a competition where you have to solve a maze autonomously. So you just basically drop the mouse in the corner and hopefully it can autonomously find its way to the center. But it's a very heavy controls concept where you need to use a lot of PID controllers, trajectory planning, and just these concepts that you might learn in classes like EE370, or if you're a mechanical, some of those mechanical controls classes. So you can apply those concepts there. If you're into DSP, there's also plenty of different designs you could do for, let's say, audio or any other devices that you're interested in doing. If you're really into digital signal processing, once you get acquainted with how to do your software and start getting familiar with different components and parts, you can easily make, let's say, something like this, which is like a guitar effects pedal, where you'll be able to program the chip with any of those DSP equations and things like that you learn in class and apply them onto physical hardware. That is something that, is entirely pretty much yours. So, just to go over the concepts that we have set up today, I'm going to give an example of a breakout board just so um, you guys have a little bit of a better understanding. Essentially, they look like this. They're small boards like this, which have, let's say, a chip or another component on it that you can connect other things to. And so they're often used in like very general things. You can buy them off the shelf and just attach wires to different things like that. So essentially, we're going to be doing that with 2 motor drivers. Oops. Um, so before I get too much into our actual design and starting, I want you guys right away to have Altium downloaded and up right now. and I want you guys to just basically get loosely familiar with placing things and everything like that, and then we'll move on to our specific design goal here. So hopefully, before today, you had downloaded Altium and had it ready to go. Initially, when you open Altium, essentially all these would be pretty much blank, so you have nothing over there. And unless you haven't already, you'll see your workspace set up right there. If you haven't set up your workspace yet, it only takes about a minute or so. It's quite quick. But this is basically setting up your drive for where you're going to hold all of your folders. So I named mine CSU Long Beach because I didn't understand what workspace was at first. So should have named it something more personal, like your name's workspace or something like that. But for example, in the workspace, here's a bunch of different projects that I have. So we're gonna go, if you haven't set up your workspace, don't worry, you don't really need to do that quite yet. But just to get started, if you have this open, and obviously your homepage will look something like this. So from this page right here, you're gonna go up to the top left where it might say either your workspace if you have, or it might just have like a folder there or something like that. If you right click up there, you'll see things that say create project. Is everyone able to get to that um, area so far? If anyone has any issues, just raise your hand, and Joseph or someone else in the back who's familiar with Altium might be able to go and help you out. So um, we're going to create a project. So this will come up with this page right here where it'll, kind of decide if it's a local or in your workspace. And basically, you don't really need to mess with anything here. Pretty much all you need to do is give a project name and quick description. I'm gonna go ahead and call this motor breakout. So this is just a motor breakout board. Um, and we can give a quick description. I'm just gonna write a small breakout board with two motor drivers for control two small motors. All right. So after that, you're going to see a new file over on the left right over here. So you'll see that this is the new file I had called just motorbreakout.prcj or yeah, PCB. And nothing, no other documents or anything like that will be in there. So to be able to add things in there to actually start your PCB, you can right click that again. And then once you've right clicked that, you're going to go to add new to project. And the first thing that we're going to be interested in adding is the schematic. So again, just right click the motor breakout project file that you just created and create a new schematic. And again, if anyone is having any troubles getting to these steps, just give your hand a raise and we'll have someone come and help you out. So once you're here, I recommend the first thing you do is save this file. You'll notice that it just came up as just sheet1.schematic document. And so you didn't really name it or anything yet. So you can click that little save button up in the top, or you could do Control S, either way works. But once you start to save it, now you can give it a name. So I'm just going to call it motor brake schematic. And yeah. So once you've saved it, you'll notice that the new name that you named it is now over here on the right. And once you have this empty schematic here saved in your project documents, we're ready to start adding some components. But before we do that, I have a specific component library that I personally really like using. It was provided via the Phil's Lab YouTube channel. So that is an incredible resource for learning PCB design and is really where I found most of my resources relating to PCB design. So I can post that channel at the end or give you guys some references for it, but it truly is an incredible channel. If you just scroll down or look up some Altium Quick Start or anything else like that, you can easily start to move to more complicated designs and get more familiar with the software. So I highly recommend in your free time also look out for those different YouTube kind of references to keep moving. But he has a specific library that has a lot of components built into it that I personally really like. So we're going to go ahead and download that and add that to this specific file. And it's a little bit of a convoluted way to do that. To where you can share it with other people. So I'll go over that part a little bit slowly. But so I went ahead and posted this link in the IEEE general chat. So I posted it right here. So you'll notice it says Altium Designer libraries, and I posted this in general. If again, if anyone's having trouble, just raise your hand. And once you're here at the GitHub, I'll give you guys a second to catch up. Oops. All right. So once you're at the GitHub, it just says, hey, personal schematic, symbol, and footprint libraries for Altium Designer. And we'll continue going over what is a schematic symbol and what is a PCB footprint a little bit later on. And we'll actually be creating our own for some of the symbols, our parts. But for the time being, you can just go up to this top right here thing that's green that says code, and you could just download the zip file. So once you have this file, you can go ahead and unzip it and extract the stuff. You can extract it wherever. We're going to be basically pulling those files into somewhere else, so you can extract it wherever you want to. All right, so once you have those extracted, you could move back to Altium and right-click this your project file. So that's going to be that top green one at the top. So right-click that, and then you're going to see the thing that says Explore, and you can go ahead and click that. And this includes all of the project files that are in your project that you just created. So you can see that we have that schematic file that we just created. We want to go ahead and move those unzipped libraries into um, this portion of the folder. And since I am using the cloud or kind of the 365 setup for Altium, this will also move those files onto that kind of cloud. So I don't necessarily have it only on my computer, but anyone else who then opens this file elsewhere is able to access them as well. So I'm gonna go ahead and move over here, and I'm gonna use. I already had them downloaded, so I'm gonna use some of my previous ones. But they essentially, after you zip them, you can go into that folder that you just unzipped, and you'll see two things that say schematic library fills lab and footprint fills lab. Both of them, yes. So once you open that file, um, you'll see that those two are in there, and we're going to want to move those into this. And I already have it downloaded, so I'm going to use the one that doesn't have the 4 on it, but you can go ahead and copy them or just directly move them over. It's up to you, but go ahead and put those files into this. All right. So hopefully by now they've moved over into that file that includes everything else. Now we need to actually make them show up here so we can access them. So in that case, you're going to right click the project file again and say add existing to project. And then it's going to open up, hopefully, the breakout board project file that you just did. And you can go ahead and add those two libraries to it. So I'm going to go ahead and go through the process one more time. You're going to right click it. And then after you right click to your project file, it's going to say add existing to project. And then it'll open up your folder, which includes everything in the project. And then you could just select these two and click open. You'll know it worked if now in the bottom folder right here, you can see both the schematic and the footprint library, and there isn't like a little white circle next to it with an arrow. If that white circle with an arrow is on there, it basically just means that it's a local version. So if someone tries to open it up somewhere else, they won't be able to see those files because those files are held locally on your computer, not in the cloud. And that's really only if you have your workspace set up where other people are working on it. So again, that was definitely the most convoluted steps of this whole process, really. So after this, it's pretty straightforward. But that process of adding libraries in so other people on other computers can see them is a little bit tricky. All right, so hopefully by now you have those in. If anyone is still having trouble, just raise your hand and Darian might come by and help out. Oh, you know what? I'm gonna increase my display size so people can see a little bit better. Good. All right. So, hopefully by now you have those libraries and everything installed. Now, what you can go ahead and do is on the bottom right panel, or on the bottom right of the screen, you'll see this thing that says panels. This is a very important tab that holds a ton of different things that you're going to be using pretty regularly. They have it down on the bottom, kind of hidden, but a lot of these things will be used fairly regularly. One of the biggest things we're going to be using is this thing, the components. So the components panel has all of the components that we have stored locally, as well as all the components that we have inside of that project file that we just created. So, for example, if we click components, you'll see basically this thing come up where it says all, and it has you might see the different, general like components that Altium has set up. However, basically the main that one that we're going to be using is the Phil's Lab one right here. You probably won't see these bottom two ones. Those are stuff that's just locally on my computer, but you should be able to see the schematic dash lib Phil's Lab dot schematic library. And again, That's once you open up the panels on the bottom right, it's in the components. And then in the top panel, you'll see this thing that says all. You can click that, and then down below, you should see that. If you don't see that, go ahead and raise your hand. Otherwise, now we can basically get started placing some components. So, by now, Darian has handed you all one of my favorite tools, which is that PCB ruler provided by the DigiKey sponsorship, which DigiKey is basically just an electronic parts distributor, one of the biggest in the United States. And on it, you'll see that there's a bunch of cool, little graphs and other information that you have on there. If you go ahead and look on, if you look on this side, so the side that has all the very small holes, right there, you'll see this like kind of big square thing in the back corner. And I'm going to turn on the video just for anyone that is missing that. So on the ruler, you'll see this general area that has a bunch of general component sizes. And you'll notice how small they are. It's pretty amazing how when you're doing PCBs and stuff like that, it's hard to grasp how small these components are because you could zoom in and everything like that. But when you kind of get it and physically see how small these footprints for different components are, then you really start to, realize how small everything is there. So, the PCB footprint is what you see right there on the bottom. So, for example, this area right here. So you see the one that has like a bunch of, it's like a big rectangle and then some smaller ones moving down. Those are general sizes for SMD, which is just, or SMT, which is surface mount technology. So any component that is placed strictly on the surface, if you see the kind of PCB robot thing that we passed around, all the components are basically on the top and they don't go through to the bottom. So the difference is through hole. So through hole means the component goes all the way through the board versus surface mount is just laying on the very top of that. So on here is, oh, where is it? There it is. So on here, there's a bunch of different generic surface mount components for passive devices or passive parts. Passive parts meaning things like resistors, capacitors, or general inductors and things like that. So these are general sizes, and you'll see off to the right that there's some numbers that are associated with them. So, for example, the biggest one at the top says 2512. Um, you see that one that says 2512. I know it's reverse on the camera, but moving down, we have 1206, 0805, 0603, 0402, and 0201. And you can see how tiny the component is on 0201. That's like a grain of sand, pretty much. That's how big the component is. Obviously, this is something that you really want to take in consideration when you're making your PCB is how manufacturable is my board? If I use all my components as 0201, it's going to be virtually impossible to do yourself. And if you want a company to manufacture it for you, it's going to be ridiculously expensive because how small those things are. Moving up, 0402 is something that I probably would not feel comfortable soldering myself. So if you're going to be soldering with something like a reflow oven or a hot plate, which we'll get a little bit more into detail near the end of the workshops on different soldering techniques and stuff. But I probably would not feel comfortable doing my own 0402s. 0603, however, is the biggest or the smallest size I would feel comfortable doing myself. And I know it looks really small, but I believe we have some people in here that were in Micromouse last year and soldered up those 0603 size resistors and capacitors that we had there. And it's a little tricky using the tweezers to place it and everything like that. But I promise you it's not too bad. And if the little Micromouse is passing around, you'll be able to see how big those 0603 size components are. Um, and then moving up, just 0805 and 1206. So those numbers correspond to how big the actual footprint of the thing is. Any of those sizes, for example, for resistors, a resistor value of, let's say, 100 ohms can be any of those sizes, really. You're not really constrained by it. So there could be a 100 ohm resistor, a mega ohm resistor, 100K can fit into any of those sizes. So that's something that is essentially just up to you when you're making your PCB. Capacitors, on the other hand, have a little bit more of a consideration you need to take when going into your footprint size and if it's actually available. If you're curious if something is available in a footprint size, you could simply search it up on a parts manufacturer like DigiKey, which we will also go into a little bit more detail later on. But for the time being, now that you roughly know what PCB footprints are, we're going to go ahead and make something just as small as like an LED circuit. So to start off with an LED circuit, pretty much, if you're familiar with some basic electronics classes, you have your power source, a resistor, and your LED and ground. So it's basically just three components of your battery, your LED, and a resistor. So let's start off with a resistor because we were just talking about that. If you go into the top, if you're in the Phil's lab portion of it, you could type it res in. And you'll see below, here's a bunch of different size resistors. And when I say size, I don't mean how much ohms it has, but the footprint of that resistor. So you'll see 0201, which is that tiny grain of sand, and then we're going to be moving up. For this project, I'm going to focus on using 0603 parts, and I would not want to go any smaller than 0603. Um, just so we can kind of simulate if you wanted to solder it yourself. So once you have that component clicked, you have a couple different ways to post it onto your board. You can right click it and you can say place the component, or you could simply just drag it over. So once you have your kind of resistor place and stuff like that, you'll notice that there's a couple things surrounding it. The first is just an R and a question mark. That corresponds to your designator for that part. Let's say you have 70 different resistors on your board. You need to know which resistor that specifically is. So, for example, resistor 1, resistor 2, 64, 70. Um, and so that is basically just a way to know which part is which, since each is an individual part. For the time being, don't worry about that because we can have the computer automatically generate annotation for which part it is at the end. So go ahead and leave the the that as is. So go ahead and double click on the resistor, and you'll notice that it opens up the properties tab. So you could do you'll notice that the properties tab is also in the panels. So if you simply just click it and go to panels, you can open your properties. So properties is one of the biggest things that you're going to be using out of the panels as well. That's why they have it set up. If you just double click it, it automatically opens properties. And you'll notice here that you have that first thing, your designator, and you have the next thing, which is a comment, and then description and design ID and some other things. Off to the right here, you have visibility. So for whatever reason, if you don't want to see any of those texts on your screen, you can go ahead and hide them. However, um, since we have the footprint size in the description, usually to make it visible to the viewer of whoever's looking at the schematic, we'll go ahead and move into the comment section and go ahead and add the resistance value. For example, let's say it's a 330 ohm resistor. And normally I will just type 330. It is a resistor, and so I don't really feel the need to add the ohms or the R's or anything like that. So normally I'll just do something like that. Um, Pretty much that's all you got to do if you're placing any sort of passive component like a resistor or capacitor. And let's move on to the LED. So Once you place a resistor, go back down into the panels on the bottom right and open up components again. Now we're going to go ahead and just look up LED. And you can see that there's a bunch of different options here. Here are your surface mount LEDs. So things that are directly on the surface. If the micro mouse board is, oh, there it is. I'm sure you've seen these LEDs in other products or anything like that, but it's essentially just those, surface mount LEDs like that. So that are just kind of on the board. But you also have your through hole, which is your traditional LED you might use on a breadboard or something like that. So um, these 5 mm ones are your through hole ones, um, and any of the other ones are going to be your surface mount. So for the purpose of this, let's just use this generic 5 mm LED generic. And if you see the THT, that usually means through hole. I don't know why there's another T at the end of it, but that's generally what I've seen. So I'm going to go ahead and move that over there. You'll see it has this LED set up right there. And before I leave the components, I'm going to stay in this components tab. Um, I'm Yeah, I thought so. All right, so I believe yes, XT60. Oops. Yeah. So the last thing I'm going to add is, let's say, just a connector for said board. So if I want to connect a power supply or a power source, usually a common thing for some bigger batteries is an XT60 connector, which you might have seen. Looks like this. These yellow things. You might have seen them on like drone batteries or other sorts of batteries and stuff. There's just these yellow little connections like that. Um, I'm just gonna place it just for the sake of doing this one right here. So all I looked up was just XT60, and that's that. So now that we have our three components placed right here, we can go ahead and start making our schematic. So, the very first thing that you want to do is just place your components in a general way that you want to have it set up. So, a good way to do it is just have things kind of linearly or just placed in a way that makes sense. And you'll notice that the positive connection right here is all the way on this side. So, if I wanted to do a connection, I would have to, move all the way across, which isn't very, helpful, or it doesn't look good. So if you click on any component, there's a couple different ways to move it around. The first thing is you can hold that component, and then as you're clicking down and holding it, you'll see it's kind of invisible like that, and you can press space bar. Space bar will flip it around the axis, and so you can flip it around, and now it's over here. However, you have another issue now. Let's say that you wanted the positive on top and the negative on the bottom. And you're like, well, if I keep flipping it, that's never going to happen. So another thing that you can do is flip the axes, like mirroring it. So if you click on it, you can press X, and that will mirror it across the Y axis. And if you press Y, it'll mirror across the X axis. I don't really know why it's backwards, but it is. So if you press X, it'll flip over that way, and space bar just rotates it around. So now that we have it face the way that we want it to, we can make like a nice even flow of our diagrams. And another quick note is just you'll notice that to move the components, there's kind of a big a jump between them. It's all kind of on a grid. Usually it automatically starts it off at the grid size of 100 mils. You'll see that on the bottom right. I would highly recommend sticking to that grid size and not changing it. However, you can press G, and you'll notice in the bottom right, it changed it to 10 if I press G, 50, or G again, 100 mils. And you might need that in rare cases that like a footprint or a schematic symbol is a little bit off grid, which shouldn't be the case. Hopefully everything sticks to 100 mils, but just a quick note on that. So, now you're ready to place all of your wires to connect things. So, the first thing that we're going to do is this is kind of in the way, but you'll notice this tab right here. And this top tab has a lot of the things that you're going to be using to actually place wires and different components and things onto your schematic symbol. So first of all, let's start placing a wire. You'll notice this one that has, it looks like a little squiggly, I guess, like a little wave. That one is your wire. If you right click it, you'll notice that there's some different options to choose, but we're going to start off with wire. And once you have that placed, you can go ahead and start connecting things. So you want your positive here, and you'll notice the big red X when you're on something. And let's move it and connect it over there. Now I'm gonna go ahead and teach you how to make wires a little bit easier so you don't have to go up and click that every single time. If you hold Control and then press W, it automatically pulls up your wire tab. So you could just keep moving, place that, and then Control W, move the next one, and it's a lot more efficient to place wires and everything else like that. So, if you're familiar with some of your basic electronics classes, I'm sure you've had an LED circuit before where essentially you hook up one side, the positive, add your LED resistor, and then the other side to ground. And we're going to go ahead and make a ground symbol that is going to represent all of our grounds just so it's visually makes sense and is in kind of the general schematic form. So I'm going to go ahead and press Control W and increase that a tiny bit. And then once you're done placing the wire, you can hit escape again and you'll go ahead and leave that kind of form where you're stuck placing the wire. And then again, right next to the wire, you'll notice that there is the ground port symbol. So if you right click it, you'll notice there's a bunch of different symbols, but we're going to stick with the ground one right now. So once you're ready to place it, just place that one down there. However, we do need another ground too. We want the negative side of our battery connection to also be connected to ground. That way it can flow as a complete circuit. So we could have a long wire, whoops, a long wire that connects oh, oops. A long wire that connects these two things. And while this is correct, both of these things are attached to ground. Oftentimes, it makes a little bit more sense as you're moving more to more complicated schematics to kind of have different areas. So these two grounds are connected to each other. So if we go ahead and click that, those two things are now connected to each other because they're both on the same net is what they call it. And I'll go over that in a second. So if we double click that, this is your wires. So if you double click any of your wires, you'll see that it comes up with this on the side that will have the physical name and the net name. So these ones don't have any names on them yet. Obviously, these ones are just connected straight to ground. So they say, hey, this whole wire is just connected to ground. And so is this one. Since they have the same net name, those two things are connected. The last thing we're going to do before we move on to actually doing our goal of the workshop is net labels. So this is something that I highly recommend everyone uses almost everywhere. So you'll notice when I click on the wires that aren't connected to, let's say, ground, you'll notice that the name is net D question mark underscore K. Which doesn't mean anything to me. It shouldn't really mean much to you. It's kind of really hard to read what these things are. And it might not seem like it means a lot right here. However, for example, as you move to a more complicated project, Um, sure, I'll just open it up. I think I have some things I forgot to net there. So, once you move on to a more complicated project and you're actually making your PCB, you'll see that when you're connecting stuff, there's all these things where it's like, okay, up here, here's my 5-volt feedback or 12-volt feedback or any of these other things. I guess this opened up a different thing, but that's for this project. Didn't realize, but um, it'll be able to tell you what that is essentially. It'll be able to point out where that net is. So this is the 5-volt power, LED and everything else like that. But these ones, I have no idea what these are. And when you're making your PCB later on, you're like, okay, I need to connect net C26 to underscore 2. And you're like, well, I don't know what I need to do for that specific thing because I have no idea really what it is. Versus this, oh, this is the connection for the low side MOSFET. And so it just makes when you're doing your PCB a lot easier to go through and understand. Um, so I'd highly recommend on this project to net label pretty much everything. So that way, when you move to doing your PCB, you're able to connect things a little bit easier. So on that same place where you found your wire, underneath here is going to be your net label. So click that and you'll see that there's this little text that generates and, just says net labels 175, I guess. And I'm going to go ahead and place two of them, one on each net. And a net is basically just anything that is connected to each other. Obviously, this wire is not directly connected to this wire, so they're different nets. So once you had placed those two nets, and I'll give you guys a second. Um, Once you guys place any of your two nets, you could go ahead and double click them, and you'll notice that it has a net name right here. And this is where you get to label it pretty much whatever you want that makes sense to you. So when you're putting together the PCB, you're like, oh, this is connected to battery positive. So I'm going to have that be battery. I'll just, yeah, I'll do battery positive, you know? And now you'll notice it says bat positive right there. And once you have that finished naming, and again, I just double clicked it to open up the properties, or you can go down to the panels and open up the properties. But now that I had named it bat positive, now again, if I double click that wire, remember last time it had the net name of like N2C, yada, yada, yada. Now it's whatever you labeled it. So this one is the bat positive. Um, and now this one is connected to the cathode side of the LED. If you have your kind of basic things as the anode and cathode side, but you could name it anything you want. But since it's the cathode side of the LED, I'm just going to name it LED C for cathode. And if I was on the other side and it wasn't connected to that, I might name it A for anode. And then lastly, this one, we don't need a net label because it's already connected to ground. All right. Cool. So, um, now that we have this circuit, theoretically, we could move to PCB right now and put this on a PCB. And we'd have a PCB that when you connect a battery that's connected to a battery that has an XT60 connector on it, it would turn on this LED. However, we want to do something a little bit more complicated that for the purpose of this workshop. So we're going to go into what we have prepared for you guys. If I can open it with all these Zoom things open. So Um, what do we want to do for this workshop? And for this specific one, we want to drive two small motors and be able to control their variable speed and direction. I chose some motor drivers that I was familiar with. We're going to be putting on essentially the exact two chips that are on this micro mouse that controls its motors. And essentially by the end of this, you'll have like, 1/5 of the micro mouse PCB done. You just have to go and move to the rest of them. But you can notice that it's controlling some of the speed and then now it's direction. So it can go ahead and turn. Whoops, like that. Or I guess it was hidden behind that, but you have to believe me, it turned. But so we're going to be putting those motor drivers on that. So a microcontroller or anything else like that can control those motors to do whatever you want to do. And once we go down the list, you'll be able to better define exactly what different motors you can choose and then tailor your hardware to exact motors or anything else like that. So, what is our desired outcome? We want to drive two small motors with variable speed and direction. The external parts that we need is a battery to power the whole thing and also some sort of microcontroller to be able to do our controlling of the motors. For example, an Arduino or an STM32 or a TM4C, any of these microcontrollers should be able to interact with our breakout board and control the speed and direction of two motors. It's not limited to any of these. So we're going to have it set up. So these are external parts that we would need for our system. So what do you need to drive a motor with variable speed and direction? So here is a very general kind of block diagram of a motor driver. A motor driver essentially is able to take low-powered control signals and then convert them to high-powered control signals that are able to actually move motors. So using a microcontroller that doesn't have a lot of power to be able to move things and things like that, this motor controller can take those low voltage or low power signals and then amplify them to be able to drive something that needs a little bit more like power or current or voltage or whatever it is. So that's what the purpose of this motor driver is. And so on the right, we'll see that we have our motor that's hooked up to this motor driver. And to be able to choose our speed and direction, we have these two inputs from our microcontroller. So we have in1 and in2. So this is basically used as like logic. So essentially, if this is a 1 and this is a 0, the motor will turn this way. And if this is a 0 and this is a 1, the motor will turn that way. And the 0 and 1s have to do with the voltage. So if you've taken your logic classes, you know it's like either 5 volts or 3.3 volts or any of those to be able to drive things like, for example, AND or OR gates. It's the same idea, except for this motor driver right here. So that's how you control direction, right? You can go ahead and move it forward or backwards. How are we controlling the speed then? The speed is using that same property of turning it on, 1 to a 0 and 1 to 1 to choose its direction. And then we can very quickly turn that signal off and on to be able to control the speed. So essentially, we're using something called PWM. And if you're familiar with PWM, great. If not, it's not a big deal. Essentially, it means pulse width modulation. So we're going to be sending um, we're going to be sending out a PWM signal from any of those microcontrollers and be able to have this. So for example, on Arduino, you can set up pins that say analog right, and then that's just setting up your PWM signal. So what PWM is pulse width modulation, meaning that you have some pulse that repeats at a set interval or frequency, and you can modulate or change how wide that pulse is. So you can do that using programs and stuff to adjust the duty cycle. So the duty cycle corresponds to how long that signal is on and how long that signal is off. For example, at 50% duty cycle, the signal is on for half of the time and off for the other half. And again, this is happening a couple thousand times a second. And so the motor doesn't really see a direct turning on and off, but because it's happening thousands of times a second, it just kind of sees it as an average increase or decrease in power. So this is the way that we're going to be controlling the speed of those motors, which we're not too interested for this specific workshop. But if you're not familiar with this, I'd highly recommend watching a couple videos or just looking into a little bit more what PWM is, because it's incredibly useful. It's used pretty much everywhere for driving motor speed or LED brightness or communications or any of these different fields. So now that we know that we can control our speed and direction with our microcontroller, um, I'm going to go very quickly into how this motor driver works. So you'll notice we have two different inputs right here. We have up top, which is a power supply from 4.5 to 33 volts, meaning that we can plug in a battery that is anywhere between 4.5 and 33 volts, and it will apply that voltage to our motor. VREF is essentially just a voltage reference to be able to know what is a zero and what is a one. For example, if you're using an Arduino, a zero is 5 volts and a one is 5 volts and a zero is 0 volts. But if you're using an STM or a TM4C, I believe it's 3.3 volts instead of 5 volts. So this V reference is just a pin that basically you're able to set what the logic high and what the logic low voltage is. So to just go very quickly into H bridges. Yeah. Oops. So essentially what's inside of that motor driver is four switches and that motor in the middle. So essentially that you have that power at the top, which if you remember, it was like 4.5 to 33 volts. So whatever that voltage that you apply here is going to be your VCC. And then down here, you have your ground. These four switches determine the flow of current, which in turn determines the flow of or the rotation of your motor. So, for example, if you apply a 1 on that control signal 1 and a 0 on the other one, then these two switches will turn on and these two switches will turn off, which in turn means current flows through here, through this motor, and it's going to spin this way and go down into ground. The next case is if this one is a 0 and this one is a 1. In that case, these two switches open up, disconnecting the circuit, and now these two close. Now, instead of the current flowing this way and going to ground, it now flows this way and goes to ground, which in turn maybe turns the motor this way. So you're able to control the direction of the motor using essentially those four switches. And that's essentially what the motor driver is doing. It just helps you out. So you don't have to have four control signals. You just have two. Um, all right. So, um, yeah. So that's just very briefly how the motor driver works. And again, if you're not familiar with a motor driver, I'd highly recommend you just watching some videos on what H bridges are or anything else like that. Because in my opinion, the theory and concept of how these parts works comes first before you go to your design. Because if you don't have a clear idea of what is happening in these parts or have any idea of like roughly what's going on, you're going to have a hard time designing it for it to work properly. I've had boards in the past where I was kind of half-assed reading stuff and kind of threw it together. And then I got it and I was like, oh, well, this isn't working how I thought it was because I just kind of assumed things worked differently and everything else like that. Um, I would highly recommend doing some research before you put any part on your board. And that's not to deter any of you from starting right away. I would still highly recommend if you have an idea or anything else to start right away to try to make your own boards. It just means that you need to take an extra step of saying, hey, let me step back for a second. How does this actually work? You know? And I guarantee you there's 1,000 resources online and tons of people that are going to be willing to help. And also, I mean, AI works pretty good at explaining stuff too. I have used it a good amount of times to help me understand some chips and things like that. This is not something that you should wait until you're ready to start doing. I would recommend that you're basically you're never going to feel ready to hop in. Just start and then go ahead and learn, and as you go you'll be like, oh, okay, it's not too bad. I would not wait to jump into it. But yeah, again, so once you kind of understand a general level of what your goal is and how exactly you're going to execute it, then you could move on to your kind of stages. So, a good way to be able to set up your goals and know exactly how to execute them is setting up your system requirements. This is something that I would highly recommend you doing before you start any PCB project. You have a goal in mind. Let's say that you want to make a digital clock, or you wanted to make a guitar effects pedal, or a board for one of the rocket projects here at school, or a micro mouse, or anything else like that. You have this general goal in mind. That's what you start off with, your desired outcome. And so in this case, we want to drive two small motors and we want to be able to change their speed and direction. So once you kind of have that general goal in mind, now you can move on to kind of describing that goal a little bit better. So for example, we want something small. So we want it to not take up too large of an area. So if we want to fit it in a small robot, or we want to fit it in a rocket or anything else like that, we want to make it a small enough PCB that it fits into that area. Next, we want to drive two small motors. Kind of already said that. The next thing, I also want to be able to plug it into a breadboard if I want to. So if I'm doing development on the ground and I have this board that we just created, we can add pins onto it and just plug it directly into a breadboard. And we're going to go ahead and do that. So that's another system requirement I want. That's something that I know my end goal, and I'm further describing what I want in that end goal. So I want it to be able to take either 5 volt or 3.3 volt logic. So we could use Arduino or STM or TM4C, and it's not a big deal. The next, I want to be able to power this with a 2-series LiPo or Li-on battery. If you're not too familiar with this means, you could also give a couple quick Google searches afterwards, but essentially 2S means 2 series. And the 2 series means 2 batteries in series. So if you're familiar with the difference between series and parallel components in electronics, parallel means they're next to each other and they're connected with the tops connected and the bottoms connected. Series means they're connected in a line. So the first one goes here, here's the bottom, here's the top. The next one goes there. Here's the bottom. Here's the top. So 2S means that there's 2 batteries in series, which when 2 batteries are in series, their voltages add. So we have two 3.2 to 4.2 volt batteries. This is just their battery range. If they're completely dead, they're at 3.2 volts. If they're completely charged, they're at 4.2 volts. So we have two of these batteries in series, meaning that our voltage input will be either 6.4 or 8.4. So our range will be between 6.4 volts and 8.4 volts. And if you just do any quick Google search of 2S battery, you'll see a bunch of different options sold by a bunch of different people, where they might look like this or that. And they're really commonly used in drones and a lot of other electronics. This right here on this board is a 2S battery. So we have two LiPo batteries that are kind of crudely electrical taped together. Uh, but this is a 2S battery right here. All it is just 2 batteries in series. So it increases the voltage because if each one is 3.2 volts on top of each other, then you have 3.2, 3.2, you get 6.4. So LiPo and Li-on batteries are really common in a lot of different robotics and other electronics. So I decided to have an input tailored for these specific types of batteries. So when I'm doing my design, I'm able to tailor it to be exactly for the battery type that I want. I want the last thing that I want is something that is kind of just going to be an extra addition thing that I thought I'd add on is current sense. So we're able to measure how much current that board is taking. So let's say that you have it in a robot and you want to say, okay, well, how long can I run this robot? If you can calculate how much current is going to the motors and the rest of your system, then you know how large your battery is, then you can calculate roughly how long that robot will last before the batteries go up. So I'm just going to add a quick thing on there for current sensing. It's really straightforward. If you're familiar with op amps or anything else like that, it's just one op amp and like two resistors. So it's really not too much to add to your board, but it gives you a lot of information that is really useful for the rest of the circuit. The last thing I want on there is just a battery power LED indicator. When I plug in the board, I want to know I want to know that it's working. So for example, for this one, I have an LED that turns on when I plug in the board. So I'm like, hey, okay, the board is working because this LED is turned on. Without something like that, it's a little bit hard if you're trying to diagnose something and you first plug it in, you're like, I think it's working, you know, like I think everything is connected. An LED is just nice reassurance as tester of that circuit is like, okay, it's good. So now that we have defined our system requirements, and this is something that I don't think is perfect. I think that we could probably improve on this. And I don't think if you're going to be doing system requirements for your own board, you're going to get perfect either. But it gives you chapters that you can kind of go through and run through. And as you design your board, we might come back and change our system requirements. But it is really helpful for keep moving forward. So if you can write down different things that you want, you can continually come back to that, reference it, and be like, oh yeah, okay, this is what I'm looking for. It's just a good way to keep your mind on track to follow the progress and follow the goal of your system. So, it's also very helpful to draw any sort of design out that you're doing, just in case. It's also really helpful to draw it out because it's easy to, you're like, okay, I want a small board that drives two motors. You could think of that in your brain, but when you go to kind of draw it out, you can get a much better um, picture of like, okay, the board will kind of be this square, right? And I'm gonna have two motors. That's a motor. I'm gonna have two motors right there. Um, and this board right here needs to connect to them somehow, right? So we're gonna have some connector or some way to connect to those motors. Maybe over here, we're gonna have one that should be the same size, but isn't. Um, Connecting to those ones. And so, boom, we have our motors connected, but what does the board look like? We're gonna need battery and the other controls. So you're like, I think the chips are gonna fit right there roughly. And where do I want the battery plugged in? If I'm going to be putting this in a rocket, I don't want all the inputs on the side because it won't fit into that small circle. So you're like, okay, now that I'm drawing this out, it would make sense to maybe put it on this so everything is linear or something like that. So here's our battery input. Um, our battery is over here. And you're like, well, okay, so now it's connected into the motors. Now we have our battery. We still need to connect to our microcontroller and everything else. And this is an absolutely terrible drawing, but you get the picture. You can kind of go through and draw it. And as you start to draw it, you can much better picture what you want your end goal to look like. If you're making it for a rocket or a robot or anything else like that, you're like, when you start kind of drawing it out, you can better define your system requirements or better define exactly what you want out of the end goal. So now that we have this great drawing to reference, I'll add it in just because. That's nice. Next we're gonna move on to hardware, and I'm gonna very quickly go over how to choose your hardware. Um, I think that we're probably going to be running out of time by the end of it, and then next time we could move on to actually placing our components and things like that. But hopefully I can teach you at least this portion. And if you want, you can go home and try to find some different hardware, something else like that. And if you want to try out something slightly different than what we're doing, feel free to, and I'd be happy to help you out designing your own board during this workshop time. So, all right. So from our system requirements, we know that we need to drive two small motors. We're going to have a voltage range of 6.4 to 8.4. And so I'm just going to go on my favorite parts distributor, DigiKey. Um, and I'm just gonna, so when you first go to their website, you could just look up digikey.com or anything like that, and it'll come up with their website, which is basically just a giant, Walmart for electronic parts. They have almost everything. And you'll notice it's kind of crazy when you start to look at things. Like, for example, if I just look at resistors, they have uh, they have 1 million different resistors to choose from. Um, so we'll go over that. So, that's a great question. How do you choose when, for example, if I look up motor driver, I'm going to come here and you'll notice I have 4,822 different options. And you're like, I don't even this too much. Um, but it's actually really easy to cut down to only, depending on what it is, you can cut it down to only be like 100 or so pretty easily. And then generally speaking, I'll just choose one that is they have the most in stock or something like that. So, started from just motor drivers. You'll notice that there's almost 5,000 of them. It's 408 or 4,822. And I have a bunch of different options to choose from there. And you'll see if I scroll down, here's all the different chips that we have. And I can keep scrolling down for a lot of pages. But we don't want to do that. So the very first thing we want to do is make sure that it's in stock. Obviously, if you're going to design something and you choose a part and then you can't order it, you can't build it. So first thing I'll do is on the bottom left, I'll click in stock and instantly we have, only 2,000 left. So that's over half gone instantly like that. Um, the next thing we can do is choose essentially what type of motor driver it is. I forgot to explain this earlier, but we want to make motor drivers for brushed DC motors. We want it to be a DC motor and we want it to be brushed. I'd highly recommend looking up kind of the different types of DC motors and stuff. So if it's brushed, brushless, DC, AC motors, just a rough idea of what those different things are, or stepper motors or anything else like that. So we're going to be using, whoops, brushed DC motors. We don't want brushless. This one also has brushed DC is a little comma. Could be used for multiple different types. So apply all. Now we're down to 700, which is still a lot. Um, Immediately if we scroll down, we'll see that we still have 700 different options. And this last step is really just dependent as you kind of look at more designs, you'll be familiar with certain companies. For example, the motor drivers that we used was made by Texas Instruments. I'm sure you might have heard of Texas Instruments before if you're in, let's say, computer engineering and you have the TM4C or anything else like that. Texas Instruments is a pretty common American, chip manufacturer. And so I'm familiar with them, and they also have a lot of really good references and data sheets online for different things. So I'm personally just choosing Texas Instruments because I like some of their previous products I've used. But I will say the Onisem and there's a bunch of other different things that work. And if you can't find what you're specifically looking for, let's say in that company, then you can go elsewhere, you know? So apply. Now we're down to 200 different options. This next option is something that is probably going to take a little bit of time to get used to, but if you scroll all the way to the right, you'll notice that there's a couple different things right here. So I want, personally, I want surface mount components. So I'm not looking for anything that's through hole because I want it to be fairly small. But that only got rid of 10 things. The next thing I want is you'll notice that a lot of these packages have all their pins kind of hidden or underneath of the chip. It's kind of difficult to solder these ones if you're doing them yourself because it's kind of hard to determine if they're actually connected correctly. Um, it's not incredibly hard, but it is harder to test and a little bit harder to do. So I want to go with something that looks more like this, where the pins are outside of it and are a little bit easier to test and make sure that everything is working correctly. Um, so I'm going to get rid of anything that is going to be any of those VFD or sorry, WFD packages or QFN. So those are different packages that have them underneath. So I believe there's QFN. I think that one is it? Any of these QFNs mean that it's kind of underneath of it. Oh, whoops, I'm doing the opposite of what I want to do. I was choosing those ones. Um, so I'm gonna choose ones that don't say QFN in it. And there's a surprisingly not there's a lot more things that say QFN than anything else. And it's kind of an annoying process for stuff like this. Um You can also filter it by the package, so you don't have to go through here, but I'm gonna do that. So now we're down to 100, and all of these ones should be, hey, what are these ones? Oh, and, whoops. Okay, I missed a couple of them, but we should have a lot more of these ones. So now that we've kind of listed down, now we only have 100 chips to choose from, which is still a lot. But I'm going to go ahead and now use our system requirements to go over the rest of them. Whoops, I clicked that one. And I personally like to filter it by quantity available, just so I know that it's going to be something that I can order again and again and not run into issues. So I want to drive two small motors. I want it to take 3.3 or 5 volt logic. And I want it to take a voltage range of 6.4 to 8.4. So I can come back here and say the voltage supply for these ones do fit. They have a current output of 1 amp. And I think this is a dual. Uh, There's a lot of pins on this one, but I believe this one is this one theoretically would probably work. It is able to output 1 amp, and you could say, all right, well, how do I decide how much current I want to output? It would entirely depend on your motors. Let's say that So, let's say you're choosing a motor like this. You can see what the different current ratings on these motors. For example, if you're using the 12-volt version, then these have a stall current of 0.75 amps and normal runs of 100 or 80 milliamps. Versus these ones have a stall current of 1.5 amps. If you're going to be using motors that go well above if they go well above 1 amp, I wouldn't feel comfortable using the motor driver that can only output 1 amp. I would want a motor driver that has a higher output. So, depending on which motors you choose, you'll be able to tailor your motor driver to be exactly for that motor. So, if you're using one of these, that 1 amp one would be perfect for it because it uses less than 1 amp in the worst case scenario in which the motor stalls. And if you're curious what stall current is, all stall current is essentially when you force the motors to stop. You can see that they want to move right now, but if I hold it, it's going to be trying to move. And so it's going to send a lot of current through there, but without it moving, it doesn't dissipate a lot of that power into rotational energy. Instead, is able to kind of go through there and almost kind of short circuit the motor. And so it'll start to heat up. So that's how much current it can take, or you're expected to see when you physically hold it or stall it, which is a real possibility in a lot of situations. So you want to be able to have a motor driver that is able to not burn up or blow up if it ever stalls or something like that. So depending on what motor you choose, for this purpose, let's say we're choosing this one that is less than 1 amp. Whoops, keeps getting in the way. Oops. Um, then this one has voltage supply. So 5 to 20 volts, 5 to 20 volts. I believe this one would probably work for that specific motor that we used if the stall current was a little bit less than 1 amp. Um, And so you can go through here and see which one kind of works best for your system. So this one can drive motors from 6 volts to 16 volts. But if you had a motor that is running off of 24 volts or 32 volts, you couldn't use this motor driver. So essentially, you have to pick your part depending on your system. So if you have a general idea of how big or what motor you're going to be using, you could then choose your motor driver. For the purpose of this, I already had one picked out. So this is one that I just used previously and that I personally liked. But you can, if you have something else, then you can go through here and choose the motor that you want or motor driver that you want. All right. So, now that that motor driver is connected or sorry, chosen, we can do our last couple things for it, which is choose those physical connectors that I drew right here, which look great. So that's going to be all those connectors for the motor, the control, or the logic. So, if I want to be able to plug it into a breadboard, I have some physical size restraints to be able to do that, right? Because all breadboards are roughly the same size. So I would want to have something that is spaced out at breadboard size. So breadboard pin spacing. So you can see, yeah, it's too that the spacing between all these, you can look up and see that every one of these pins is spaced 2.54 millimeters apart from each other. So if I want to be able to plug it into a breadboard, I can have these holes spaced at 2.54 millimeters. However, I want to be able to kind of make it dual purpose. So if I want to plug it into a breadboard, I can. However, if I want to have a connector to it, I can also choose a connector that has pins spaced at 2.54 millimeters. And I'd highly recommend just looking into JST connectors. Sorry, that's hidden. Let me move it over. JST connectors are kind of a general purpose connector that you'll see being used in a lot of places because it's cheap and easy to implement. And so you might have seen connectors like these used all around. And there's a bunch of different type of JST connectors. So you can see that there's a small ones that the pins are spaced 1 millimeter, 1.25, 1.5, or 2.5, but there's also JST connectors spaced at 2.54 millimeters, which are the exact spacing of a breadboard, meaning that those same holes that we're going to be putting on our board to be able to attach pins so you could plug in a breadboard, we could also swap, instead of attaching pins to plug into a breadboard, we can attach a connector so we can connect to it. So it's kind of nice if you're making a breakout board to make things that are spaced at 2.54 millimeters. So you can plug it into a breadboard for easy development and stuff like that. So I went ahead and already found some JST connectors for the motor connectors. But the next thing you have to decide is how much power can those motors take? For example, if you're using um, one of these one of these JST connectors, which are tiny, um, could you power a motor that is going to move like a tank or something like that? Obviously not. So you need to be able to choose a connector if it's going to be powering something that needs a little bit more power. You need to choose a connector that is rated for your specific setting. And every single type of connector and wire will have current rating and voltage rating. And you need to make sure that you're following those constraints before you implement them on something, because if you're using a wire that's only rated for 60 volts and you're using it for like, let's say 120 or 300 volts, that wire could actually fail. And, that could be a very big problem to the rest of your system. So you could simply look up JST 2.54 millimeter of voltage current rating. Whoops, rating. So it's able to withstand a voltage of 250 volts and a current rating of 3 amps. If we're choosing the motor that we had chose before, which runs at worst case scenario a little bit below 1 amp, this will work perfect for us. So that's just something else to take into consideration if you're going to be using a connector, is how much power can I actually put out of this connector and how much voltage can I run through it. So we know that this connector that we chose is able to withstand the power of our motors. So we just double checked it right now. And these rest of the connections are lower voltage and lower current than the motor. So we don't really need to worry about them. The next thing is the battery connector. If you remember earlier, I looked up 2S battery, and there is a ton of different options that you can choose. However, one of the most common connectors that I see on these are those little yellow connectors like that, right? They're almost on all of these batteries. So, for example, if I click on this one, it has that little yellow connector and also a small JST, but that's mostly for charging. But let's say that you want to plug it in using this yellow connector. On any of these things that tell you the battery, they should be able to give you information regarding the plugs and things like that, because they want you to use it. They need to know that you have something that it can actually connect to. So the discharge plug, which is the plug for the battery, is an XT30, which is essentially, if I look that up, just a smaller version, uh, not a camera, is a smaller version of the XT60 I showed earlier, where they look like these little yellow connectors. So if I want to be able to plug in a very common 2S battery, I can choose a connector on my board that is able to plug into a lot of different batteries. Personally, I chose this little side mount one just because it's a little bit easier to plug in onto PCBs. And lastly, I chose an IC to be able to do the current sensing. I know we're at the last minute here, but next time I want to finish. I guess next time we'll start doing the schematic for this specific motor driver, and and then be able to describe or be able to do pretty much all of this next time on the schematic. And then we'll also go into the design of the current sense amplifier that we're going to be putting on there. So hopefully by the end of next time, we'll be pretty much almost completely done with the schematic. And then we'll be able to move forward with the PCB. That is all I had for you guys for today. I can post this document on IEEE Discord if you guys want afterwards. If you have any questions, I will stick around for a couple minutes, but other than that, yeah, enjoy the day. Cool. Wow, damn. Yeah.
See you guys next Wednesday for session 2, same time.